Okay, so here's example 2 from, it should be class 16, I believe is what we decided to call it. Yeah, and actually, it's kind of an extension of class 15. We did this same example, but we had, I say it's modified. I don't know. Oh, I guess I just did it for a full rotation. And I think I decided also to do it in the positive direction, even though they're showing it in the clockwise direction. Counterclockwise is going to give us, it's just going to be easier for us to do for a full rotation. So what I'm going to do, so I previously done this in Excel here, and we got to this stage. What I should have done, I think, now that I think back at it, it would have been good if I had, because I modified the full rotation, right? I modified this crank slider, and then I did a crank slider and a full rotation, and then I did a crank slider with velocity, but I did those velocities based on taking the differentiation there. But what I could do instead, I'll go ahead and stick in 2 rows right here. I could have just as easily, we'll move these to the right, done it by with the equations. That would have been good. So right here, numerical differentiation is what I'm going to call this. These 2 columns, and here we're going to we'll get the exact same thing here, right? Except that we're going to use the equations that we had. So the equation for omega 3 is to take A, by the way, F4, make sure we put F4 here, and multiply that by omega 2, also F4, and divide by B, F4, and now we're going to multiply that times the sine of theta 4 minus, I'm sorry. I messed up. I should redo this whole video, but I'm not going to because I'm too lazy. What I should have done here, you know, all of that is fine right there. Actually, all of that is okay. I just did it in a different order than we're normally doing it. So I'm going to multiply that by the cosine of theta 2 right here. Okay, and that's going to be in radians already. That's fine. And divided by the cosine of theta 3, which is right here. And then once I have that, I can find that what's called d dot, or actually is VB for us. And we're going to take negative A times F, and make sure we do the F4 there, and times omega 2, right? And that's also constant, so it's F4. And then that's going to be times the sine of omega 2, not omega 2, of theta 2. That should be this guy right there in radians. And that does not have an F4 because it says it follows along as it gets put down there. And then we had plus B, F4, times omega 3, which is what we just calculated, times the sine of theta 3. And none of those have an F4 in them because, or not, neither of them have an F4. The omega 3 changes, and so does the theta 3. Boom. If I copy this, I'll just copy this down to the next cell. Yes, that's the ones that were, so it looks like it's working correctly. And we can plot those side by side in here. So we wanted to actually add this in here. And we should actually give these things names right up here. So I'll put a name here in a second. And then I'll go for this is going to be versus time, right? And I could actually have it for 0, so I will include the 0 in there and come all the way down. That's great. And then I want, what did I it's only VB that I really care about, right? So let's see. Scroll down all the way down to there. I am recording this, right? Seemed like it. Losing my mind. Okay, so I should have let me edit this and give it this thing a name. All right, so great. And this guy's name, I'll go these. I'll just equations. I spell equations, right? Yeah. And let me merge those cells over there. Give all these things little borders. It looks nicer that way, I think. I like these to be in the center. Okay, and then so we're going to be able to do then is to do the MATLAB, or excuse me, the SolidWorks, and then the MATLAB, and make a comparison. When we put these two on top of each other, we can see that they're very, very close. So we want to maybe try our best to see them one on top of another. It's better if they're thinner lines. And the equation is like the main one, so I'm going to keep that one. See, I can't select it, so I got to go there. I'm going to keep that one as like the bold, but I will do numerical differentiation there. Make that a thinner line too, but I'm going to make that one dashed, right? So that you could, now you can kind of see one on top of another. And by the way, later on, we might want to, I'm not going to keep this information here, but let's just take a look and see the difference right here. So we could take, and we're going to treat the equations like the one that's correct, and all the others we're going to compare to them. And it should be, I think, it should be correct. We can see that that's turn it to a percentage, give a couple decimal places, boom. And we can kind of see how it wavers. Okay, so the numerical differentiation doesn't really do, and of course we got to be careful. The last one is always going to be wrong, right? So the last one is always wrong, and we'll see that with MATLAB as well, but not with SolidWorks. And we should really put a legend on here. So, oh yeah, here's what we do. We go to here, format, and no, we go to design. And legend, and I don't like that they only give you a couple choices here. I'll put it there on the bottom, but I always bury it inside, next to the into the thing, and try to find a place where it isn't crossing over the graph. Down here is a pretty good spot, probably. Usually, like what I'll do is I'll give it a fill. Fill it with white so it can stand out on top of the grid lines. If you keep the grid lines in there. Grid lines aren't really necessary, in my opinion, if you aren't going to be picking numbers off of the thing. If you just want to see the relationship between stuff, you don't need to put grid lines in there because you're not like picking numbers off. But you know, sometimes they look kind of nice. So what we want to do now, okay, so this is something that we could have as part of our discussion, to say the different percentages that they vary between things. You'll notice that they get really large percentage difference when you get closer and closer to 0, because they could be just slightly off. But this right here is where a lot of the knowledge takes place. I'm going to get rid of it for now. We could go back and do that because I want to put them side by side for the results of my my MATLAB, excuse me, my SolidWorks and my MATLAB. So that is the solution. I don't think there's anything else I need to do. So I'll continue with this video because it's not that long. It's not going to be as long because it's only 9 minutes into the thing. So here is the part that's built in SolidWorks, right? So I built these parts at the correct proportions, and on the piston thing, I put a little I put a sketch on top of it and then put a point on there so I could use that in my motion study. And have I created a motion study yet? Yes, I have. So I'll create one from scratch here. You'll note that I think I put it in there. Yeah, I made these parallel, right? So I made a surface on top of this and the surface on top of the ground parallel. So it will start in the 0, theta 2 equals 0 position. And so I'll create a new motion study here. And much of the same things that I've done in the other example right here. So I should probably not give you this example too, so you don't have a step-by-step thing. But if you want it, this is what I put in here. And so let's see. So for the this, we want to give this we decided a counterclockwise on the RPM. Was going to be 30 radians per second, which we could calculate ourselves to be 286.5 RPM. And everything else, are we good to go? Yes. And if we wanted to get this thing for 3 rotations, we're going to move this down. I calculated 3 rotations to be 0.6283, so somewhere down in here, and come back out. There we go. Come on. Let's see. 0.6283. So 0.625. So 0.63 would be good. 0.63 is good. Yeah. And let's see. Let's also, we could go ahead and solve the thing right here. Let's see. Boom, 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 boom. So we can take a look at it. Right. And of course, if we get plot the velocity of this thing, or you plot the results, I want to get this stupid thing out of the way. I don't know why it pops up. I think it must be it didn't used to pop up, and I don't know what it is there. Let's see. Oh, you know what I forgot to do in the other one? That's too bad. I forgot to show you this. So I'll show you this thing. It's actually kind of neat right here. So we want to have only the x component, and we want to pick that point. Boom, right there. So we have something to reference here. We want to create a plot, but also show the vector. That's kind of a neat thing to do. So that arrow shows up onto there. It's got a nice little visual thing when you're making an animation. So you can see that it's pretty poor here in terms of the velocity. Let's fix the number of steps. And I figured that we needed 343.8 steps per second for the 5 degree steps. That's what they had, 343.8 steps per second, and we can't do fractional ones. But so 344 is the best we're going to be able to do. So let's try it out and resolve it that way. And check out that arrow. Isn't that cool? It's going to be even better when we have acceleration to add that vector thing into there. And look how nice and smooth that turns out to be. And in the results, we can go ahead and export that to a spreadsheet. Oh yeah, I did it. There you go. Yeah, I forgot. It opens it up. I was looking for it. All right. And now we could take time versus this velocity. And you know what? We could have also gotten omega too if we wanted to. Let's actually do that. I'll finish this thought right here, but we want to, we could put that right into here. Boom. And maybe, let's see. Should have fixed the sig figs here. Well, I guess I could just go ahead and make this thing wider and auto fit the columns there. There you Well, yeah, let's see. We could plot that on top of there. So we can select the data. Well, let me put it up here. Let me put it down at the top up here. Let's say SolidWorks on top of here, and this is going to be time, and we are going to plot it. So like I could go ahead and plot this, but let's do it all the way through. We go to I'm gonna let me get out of this, and here let's also put for on this graph right here. Let's plot the graph. We will put displacement. Let's put the angular velocity, and now it's going to be of this piece right here. I think that's going to work, and we're going to add it to the existing plot, which is right here. Now that's going to be a totally different thing. Like, well, this is millimeters per second, and we're going to have radians. But let's put it back on there. Is it giving me a hard time? Oh, I'm going to select the component. We just want the magnitude of the angular velocity. I don't even know what the hell they mean by the x and the y. But we're going to see right there. Actually, let me think about it. We might actually want that to be about the z, right? Because they gave us a magnitude, so it's not going to be negative. That's the issue I have right there. So let me see if I can fix that. And let's take the z component. Let's see. Is that going to be the correct one? Yeah, I think so. Yeah. All right. So now when I come down to here and I can export it to the spreadsheet, it's going to have angular velocity in, oh, these are degrees per second. That's interesting. And what the hell is going on right here? Oh, it's getting mad at me. Oh, okay. I guess it had to graph the thing. That was weird. All right, so we're going to have to rearrange this. First off, they're in the wrong order for what we were using over here. But they are saying degrees per second, which is an interesting variable. So we actually, yeah, I'll copy it over and then fix it when I get into the because I am going from one computer to another. We're going to have the issue again. Oh, damn it. We're going to have the issue again where we have to, where the time isn't going to be correct. So I'm going to copy this back over. So we're going to copy it right there, but we have to do some manipulation here first. First off, I'm going to move these guys over one. And let me, I think it's the number of decimal places here. Yeah. And these are in scientific notation, and the other ones aren't. So let's put those into just right into numbers, just numbers with a couple. There you go. Yeah, maybe get rid of some. Okay. And so this one is degree. Let's say we're going to divide. This is equal to. Let's see, that definitely divided by 3, no, divided by 180. That's right. Divide by 180 and multiply by pi. And boom, all the way down. And what I'm going to do is I'm going to copy this and then I'm going to paste as values because I don't really have any need to have this around. Whoops. Did I do that right? Yeah. Yeah, I could get rid of both of these columns. All right. So this is the SolidWorks one right here, and we will merge that right there. And then I might want to get rid of some. Let's see, I'll format just a little bit. And we could check them out. We could see we're not too bad off when we get to this, and we could plot the SolidWorks on top of this too, right? We could go add, and we'll get the name SolidWorks and put the time in here. and a 20-minute video. Here's a VB. And let's check it out. Now, I don't really like the gray. Let's go to green. Let's make them thinner, and you can make them dashed. Yeah, you can't quite see the difference because they are very close to each other. So this one's tough to really make an evaluation just based on a graph of them. They're very, very close. One thing I didn't mean to do right here is I did mean to bring this one up, right? So the equations should be the top one right there. So I made that one the first in terms of here. But yeah, what we could also do, I mean, if we wanted to like try to have some kind of like understanding of the thing, is we could have these percentage differences, right? So we could take, and I shouldn't do the first one, I should do this one, equals, and like I said before, we're going to use the VB right here as for the equations as the go-to. So this is the same thing I had before. I should have probably left it there, but I didn't. And that's a percentage and maybe only one decimal place. And I'm going to copy it over to here, but now it's going to be, I want to do this one and that and that. Okay. So we can actually see that what these things are and kind of check them out, right? And we can plot that versus time too. We're going to see that we're going to have little bumps like right there. We get to, I don't know if plotting it versus time is going to matter, but you're going to see that this is really the transition right here between negative and positive. So it passes through zero. It does the same transition right here, but because it's so that there is a difference right there, and there's such a small thing right there. There's such a small value is divided by, so that it ends up being a large percentage right here. So just be aware that that's that's the reason why it shows up right there. But for the most part, they track pretty well, and it'd be interesting to take a look at compare the time of the SolidWorks to the time of the. So let's do that actually. So what is equals the time that we find right here minus what we have in SolidWorks. Boom. And let's turn this into a scientific notation because it could be pretty small. It'd be nice if it was really, really, really small. Boom. Yeah, you can see that's a pretty small number right there. But it is accumulating. The difference is accumulating as you go through. You can kind of see that it's still itty bitty time frame. So it still probably can do a decent comparison at the thing. And of course we go back to that's what degrees we want, 60 degrees, and make that comparison. So that should be pretty close to being 60 degrees. And you could see what we get in SolidWorks versus numerical differentiation versus equations. And so there's the understanding. I'll make a separate video for the MATLAB. I'm not sure I even have written that yet, so we'll see. So do I want to stick anything on the end of this video? I think I've run out of guitars that are out of their cases right now. So, and I think I put a ukulele on one of the other videos here. Okay. So, I have a bunch of small guitars. Oh, you know what I should show you? Ukulele Base. violin ever. So here I am, stumbling around. So this is really cool. I like this one. A ukulele base. Can you believe it? Camera. All right, so check him out. This is the Kala base, right? They called a U base. See, it's hard to see. The light is, and it's got rubber band strings. And it's out of tune. And you can plug it in. It is electrified. There's not very good electronics in here. It's just a path. Usually have an active pickup when you have. And I'm crushing the cable. So let's see. So really should be tune that thing. I was going to tune it the wrong way. So you use a tuner for too long, then you can no longer tune by ear. I think I just noticed the other day that I played the same bass and the same stuff on one of the videos. I'm going to get rid of this stupid thing. How do you get rid of this? Video. Yeah, I think that's where I switched to photo mode. So you can see the stuff on the ceiling a lot better in this one, this camera right here. You see I changed my EVH banner. That's the word I was looking for. The word banner. I couldn't remember the word banner. All right, so that's this is today's ukulele bass. It's very cool. Does it count? I think it counts. Does it count? Is it ukulele? Is it a bass? Is it a guitar? Does it count as a guitar? I don't know. Maybe. We'll see. So until next time, thank you. Oh, you could draw on this. Interesting. Can I draw on this? I go. Oh. There you go. Getting weirder and weirder. Each one getting a little stranger.